Hello everyone, this is Thiagarajan, a retired Deputy Chief Engineer from Indian Railways. So this video, let's see something about the traction and the tractive resistances connected to the railways. Okay. First we will see the laws of motion. You know well about the Newton's first law of motion. What it says, the state of any object which is at rest or in motion remains same unless and until any external forces act on it. Okay. Suppose let us take an object which is on a level plane, so it will be static as it is. So unless until any external force act on it. Suppose we are applying some force on that, it will start move, but even then for some distance it will go and it will be stopped. So because of the force acting against the direction of the motion, okay, that is on the surface, that used to say opposing force, that is because of the friction between the body and the surface. Okay, because of the friction resistance, okay, the moment is gradually reduced, the motion speed is reduced, and finally it stopped. Okay, so that is all because of the condition of the surface and the body surface. If it is a rough, the movement will be only for less distance. If it is smooth, it will go for some distance, it will stop. So it is based on the roughness and smoothness. You know pretty well the roughness means what? There will be the minute undulations will be there. There will be ridges and valleys, both surfaces, body as well as the surface. So it just when it is just rubbing each other, there will be friction resistance. Sometime or something just gets locked and it stopped. Okay. This is something about the frictional resistance, frictional force, which is acting in between the body which is in motion and the surface on which it is moving. Okay. Coming to the types of frictions, we have sliding friction, rolling friction, limiting friction. So sliding friction is what? That means a body slides over another. Okay. That what you have seen earlier. The rolling friction means what? This is the wheels of a moving train on rail, or the car wheels, moving on a road. So that is all rolling friction. Limiting friction, of course, it is generated between two static forces come in contact, which is static, which is stationary. Okay, that is limiting friction. But we are concerned about the rolling friction, and the sometime sliding friction also will come across. Okay. So coming to the frictional resistance and a pulling force, see, so this is the body which is on a level plane, and the weight of the body, let us take it is W, and as already discussed, there will be frictional resistance which will be acting opposite to the movement of the body. Okay, that is because of the friction between the body and the surface. Okay. So in this condition, how much pulling force required? Suppose we want to move the body, we require some force move. Okay. It is all based on the weight also. More the weight, more force required. Lesser the weight, less will be the force. At the same time, the resistance also coming to play. That means more the frictional resistance, so more will be the pulling force, and lesser the frictional resistance, it will be less pulling force required. Okay. So that means in case of surface is rough, it requires more pulling force than if it is a smooth surface. Okay, all know, because if you take a car having the rubber tired wheel, and you have to apply more force to push it, then suppose if you have the wagon having the steel wheel on rail, it requires less force to push because of the surface condition. Okay, there it is smooth surface, here road surface is little rough as compared to the rail. And coming to the let us take a body, a vehicle which is fitted on the wheel, okay, having the weight of W. So for making the entire body to move, how much tractive force is required? That means pulling force is required here. Here it is fitted on the wheel, because it is a rolling friction here involved. Here it is sliding friction involved. Here our people of ancient, they invented technique of using a circular wheel fitted on the vehicle for easy transportation. Okay, even now we follow this technique, and here because of the wheel having the less contact area, it's having less friction compared to the here entire the complete portion is having the contact, because the contact is more, that is why the more friction resistance will take place. Here it is only the very less contact area, so that is why here less friction resistance involved, and we are able to pull it easily, applying a little amount of force compared to this type of sliding friction. So actually here the amount of tractive force required for making the body to move, we have the expression P equal to W into mu. W is the weight of the body. Weight of the body, it's transmitted through the wheel, okay, and goes to the rail surface, and the mu is the coefficient of friction. That means the frictional friction which is taking place between the contact area of the wheels and the surface of the rail, and we consider as a mu. Okay, we used to say denote as coefficient of friction. So the total application of force, total force required, tractive force required for making the body to move, P equal to W into mu, where W is equal to weight of the vehicle and mu is equal to coefficient of the friction. Okay. Okay. Coming to our the main subject, see the hauling capacity and the tractive force required for the train. Let's see something about it. And this is a train formation. This is a train formation. This is locomotive. So this is called a traction. So this is only okay, having the propulsion to move the entire train formation. Okay. So we used to say it is a locomotive, and we have different type of locomotive we have. Actually, those days we have steam locomotive. So now it becomes obsolete where it is used in Indian Railways, and we have right now diesel locomotive and electric locomotive. In major we are using electric locomotive. Diesel locomotive also gradually now reduced. Okay. Even the locomotives we have different types according to the hauling capacity. Okay, it is all there. So this locomotive is only having the driving wheels. Okay, such with motors, and the entire load of locomotives will be transferred to the driving wheels. Okay, wheels. Sometime there will be all will be driving wheels. Sometime it will be two driving. Some out of 6 there will be 4 driving wheels will be there. Okay, it's according to the type of locomotive. Okay, so here we have the locomotive, that is traction area. Then we have the compartments. So normally we have passenger trains and goods train. Okay, locos normally attached with the compartments, coaches for passengers that were carrying passengers. Okay, then and we have the goods train also. Goods train, that is we have the wagons, goods wagons loaded with the heavy consignment for transporting this goods, and a different situation, and according to the the capacity, according to the load, according to the section concerned. Okay, this locomotive will be decided. What type of locomotive has to be used. Okay, that will be decided. Here we see, here only the we have driving wheels. So entire road is transferred to the driving wheels, and because of propulsion it starts moving, and and because the friction between the wheel and the rail, it has the grip and gaining the momentum. Okay, here you can just see this portion we need friction. Some friction is needed on the surface rail. When there is no friction here, it's completely smooth. It's completely, let us assume that is completely smooth and oiled, and there is no friction. What will happen? Even though you just having motor and the wheels are rotated, so because there will be slippage. Okay, it cannot haul, it cannot gain any momentum. Okay, that minimum friction is required, and based on the load also. So more the load, so it will be acting. More distribution load will be wheels, and because of the friction and the surface of the rail, it will get more grip and try to propel and move forward. Okay. And the rest of the portion, the coaches, the compartments or the wagons attached with the locomotive, that is not having any driving wheels. So that entire load will be hauled by the locomotives only. Okay. Here we must understand, we must know how much tractive effort required for pulling the coaches behind the locomotive, whether it is compartments, passenger coaches or goods train wagons. Okay. So as already discussed, then we have to use this relation. The hauling capacity locomotive equal to coefficient of friction into weight on the driving wheels. Okay. Here let us assume it is total load, weight of the locomotive and all are transferred to the wheels. Okay, let us assume all 6 wheels are there, 6 pairs of wheels are there. All 6 pairs of wheels are driving wheels, let us assume. So the coefficient of friction, let us take it is a mu. So the hauling capacity equal to this mu into number of driving axle into axle loads. Mu is the coefficient of friction and we have the number of axle. Okay, we have to take the 6 axle we have, so into axle load, that is mu into number of driving wheels into axle loads will be your hauling capacity. Okay, this is something about the expression to find out the hauling capacity of the locomotive. And here you see where the mu, as well as in our case the rail wheel interaction, you see we are normally considering which varies from 0.1 to 0.2. Okay, 0.1 to 0.2. For average dampness condition it is 0.166, because sometime there will be wet, sometime it will be more dry also. Dry condition and wet condition it will be different, and sometimes it will be oily surface, sometimes it is because of fog, the snow area. Okay, so our various conditions, this will vary. However, the average conditions, average dampness condition we consider as a 0.166. Okay, this is about the coefficient of the friction. So using this expression we are finding out the hauling capacity of the locomotive. Okay, accordingly we will decide the number of coaches, compartments attached to that, or the goods wagon loads will be decided. Okay, and further I want to say about the locomotives also, we have different types. So of late we are having only broad gauge, so meter gauge is not there. That is why I am just mentioning only the broad gauge locomotive type. So W meant for actually broad gauge, and D meant for diesel, and M for mixed. That means this is for goods or passenger it can be dealt. This locomotive WDM, and WDP it is only for passenger trains only. So diesel passenger broad gauge. Here diesel goods train, it is only for goods train, for hauling the heavy loads. So WDG locomotives are used, and A meant for AC locomotive. So it is a broad gauge AC locomotive mixed, and broad gauge AC locomotive for passenger, broad gauge AC locomotive for goods trains. Like that we have different type of locomotives, so named this way. And even these locomotives are having some subcategory also, 1, 2, 3 like that, according to the hauling capacity. Okay, so this is something about the hauling capacity, how it is arrived. Okay, but once hauling capacity then we can find out how much load it can carry. This it will be deciding based on the the particular section. Sometime not only though we have the hauling capacity, and we have the coaches, and we have some resistance also. So not only you have to consider the load of this one, coaches are the loading condition, but also because of there will be friction. Okay, it has to overcome. So various frictions, and because of there will be some resistance. So considering this also we have to decide. So how much load this particular loco can carry, and what speed should run in the particular section. So everything will be decided. So that we are going to see in the coming slides. Okay. The earlier we have seen about the hauling capacity of the locomotive, and based on that how much load the particular locomotive can haul. So we can calculate. But another thing is while we are deciding our the total load to be carried by the particular loco, we have to consider the other aspects of the resistances, because though the entire formation with the loaded condition on rail, so there will be some resistance, okay, because of the various means, because maybe due to the rolling stock, because the rolling stock, the inside parts, and there will be some resistance, and because of the track irregularity, some resistance will be there, and atmosphere resistance. So all those things we have to consider. So to go in detail, particularly in the rolling stock resistance, so because maybe due to the journal frictions and rail wheel friction and other internal parts frictions of the loco and vehicles. So for example, this is your bogie of the coach. So we have the journal. Here journal will be there. Nowadays we have, earlier we got journal, some plate will be there, oiled plate, and now we have roller bearing also will be there. So because of the some amount of resistance will be there. So it was to overcome this resistance also. And rail wheel friction, because of the wheel having the contact with the rail, there will be some friction, and the other internal parts. Okay, so considering all those things, this has been calculated as the rolling resistance, rolling stock resistance equal to 0.0016 W. It is only depending on load, depending on the load. Not depending on the speed, depending on the load only. So then coming to the track resistance, so track always, there will be some irregularity will be there, like there's some undulations will be there. Because of the undulation, there will be roughness, some frictions will be there, some resistance will be there. So okay, so not only that, and whenever the trains are running in even a straight track, there will be sinusoidal motion always will be there, because we have the coning of wheel, and always this flange will be guided by the rail. It will hit and it will come this way, like that. So there will be some nosing effect will be there, because of some friction will be there. So considering all those things, that resistance due to track, it has been calculated as 0.0008 W into V. So it is depending on load and also the speed. Okay. So this is another resistance we are supposed to consider. And atmosphere resistance, okay, when the velocity is zero, stand still. So even then, when the trains are running in a speed, so there will be some resistance, okay, because of the air in the atmospheric conditions, okay. That has been calculated as 0.000006 WV squared. It is also depending on the load as well as speed. Speed square the speed. More the speed, more will be the effect of atmospheric resistance. Okay. So these are the resistance we have to consider, and also due to the track profile. So track profile means what? Always our from, suppose if you take a section X to Y, that will not be an horizontal plane. Always there will be a rising gradient, falling gradient will be there, because of the topography. You are supposed to follow the profile, considering the optimized cost of constructions. Okay. So necessarily the train has to climb some steep gradient. When it is climbing over the gradient, there will be some resistance because of the gravity, push, pull. There will be some resistance it has to overcome. Another thing, because of the curvature also. So whenever it is negotiating the curve, so it has to always there will be angle of attack. The outer wheel have the contact with the outer rail. It will be rubbing against outer rail always, because of the fixed wheelbase. Okay. So every point there will be angle of attack, and there's a torque. And because of there will be friction. Normally here in this case it will be sliding friction. Okay, so that also we have to consider. Okay, it will be based on the curvature. Sharper the curvature, more will be the friction. Okay, so this thing also we have to consider. If you want to go in detail about the gradient, you see here, this is your gradient track, and okay, this will be the normal position, this will be the vertical to the horizontal. So whenever there is a movement is here, okay, the load will acting downward vertically, but to the normal the angle will make us a theta. So if you take this triangle, this theta equal to this triangle, this theta is equal to gradient because of the gradient, gradient. See, so because similar triangle we can just equate and we can have the relation. So we have to find out this resistance due to the gradient. So in this triangle, resistance due to gradient equal to how much, we have to find out. That we can take this triangle, this sine theta, and take this triangle, sine theta is equal to opposite side by hypotenuse, opposite by hypotenuse. Opposite is by RG and hypotenuse is W. But because of the angle is very, very meager, now we are considering a sine theta equal to tan theta, approximately, not much difference. So tan theta is equal to RG divided by W. Okay, RG divided by W. So equating this with this triangle, okay. So W, RG equal to W into tan theta. RG equal to W into tan theta. But whereas this tan theta is equal to nothing but the gradient, 1 into 1. Tan theta is equal to gradient. Because for 200 means, suppose let us take, gradient. Suppose let us take this is your horizontal distance, this is vertical distance. For suppose let us take 1 into 1 to gradient, 200 unit gradient, 1 unit rise is there. That means tan theta is equal to opposite side by adjacent side. If it is 1 into 200, 1 by 200 will be for tan theta. Okay, so like that we are getting the expression here. And also I just worked out some example also. If the relation resistance due to gradient equal to W into tan theta, suppose in case of 1 into 200 gradient, 0.5%, and load of 20 tons, how much it is coming? RG into W into the gradient, that is tan theta, W into gradient. So that is equal to 100 kg, okay, for 20 tons. If it is load is acting on 20 tons, that resistance will be 100 kg. For 1 ton, it is 5 kg resistance will be there. There will be loss of 5 kg. So this resistance also we have to consider while designing our total load to be carried by the particular locomotive. And coming to the resistance to curvature, because of the curvature, you see here, this is your curve. This is inner rail, this is outer rail. So always, whenever trains are negotiating the curvature, so there will be some resistance, because this bogie type, we have the train formation, and each compartment or wagon will have some bogie arrangement having the fixed base. So always, there will be angle of attack. Every point there will be angle of attack, because the fixed well piece, it just the front wheel, okay, outer rail, there will be always contact. We'll just hitting and taking the turn. And also one thing, another thing, this inner, this inner wheel, this outer wheel, because of the curvature, if you take a 2 point, this X and Y, the inner length of rail will be lesser than the outer rail. Outer rail length will be more. So the outer wheel has to cover longer distance than the inner rail. So though we are having the coning of wheel, everything, so because of the differential length, there is some resistance will be there, some slippage, some interaction, more interaction will be there. So all those things we have to consider. There will be some additional frictional resistance when the vehicles are negotiating on the neck curve. Okay. Here you see here, this is supposed to be take, this is R. If you take a central line of the track, let us take it as R. This length will be R minus G by 2 into alpha. That means what? When you take 2 points here, means date is where you are drawing, is the angle subtended center. No, this will be angle subtended theta. The arc length equal to radius into angle subtended center. Suppose for center line of track, the arc length will be equal to r into alpha. Okay, that will be the total distance along the center line of the track. Suppose if we want to know about the inner rail of the track, r minus g by 2 into alpha, that will be the length of the track to be covered in inner rail. Outer rail, it is r plus g by 2 into alpha. Okay, so because of the difference in length, so there will be some differential movement, and thereby there will be some resistance. So the more the gauge, more will be the resistance. Okay, like that, curvature is sharper, the more resistance will be there. Okay, so from there now we find out that we got the expression RC, that means resistance due to curvature equal to F into G dot by R. F means what? That is sliding friction, and G, that is gauge. Okay, and R is a radius. Suppose here let us consider it is a constant. Suppose we are having only for broad gauge. Suppose we broad gauge and mid gauge and narrow gauge will vary, but now we consider only for the broad gauge. So that sliding friction into gauge into R. Then curvature is sharper, that more will be that is inversely proportional. So here the relation, the expression is RC equal to F into G dot by R, where F equal to sliding friction and G equal to track gauge and R is equal to radius of the curvature. But so based on that, this expression had been further reduced to 0.0004 W into D, where D equal to degree of the curve for broad gauge, and for metric gauge 0.0003 W D, and for narrow gauge 0.0002 W D. So it is based on your load as well as the degree of the curve. Okay, degree of the curve. So sharper curve, more resistance will be there. Okay, and also load also playing the role here. Okay, so and also if you see an example for curve of 2 degree for load of 20 tons in BG, so this resistance to curvature is equal to 0.004 first case into 20 tons converting into kg into 2 degree curve equal to 16 kg. Okay, suppose for 1 ton how much? 0.8 kg. So this will be your expression for how much load, total load na, for that we can calculate how much load, for that how much loss will be there. Okay, we can reduce. So this is all because of the resistance to gradient and resistance to curvature, we are supposed to follow that. Okay, so now we can see some of the other tractive resistance also we can see now. So resistance due to starting. Okay, during the starting, so static to gain the momentum, some effort is required, so there will be some resistance. So for locomotive alone, 1 and 1 W1. W1 is only weight of the loco. So it is for locomotive only we have to consider, and other for vehicles, for that is for vehicles 0.005 W2. Okay, this thing we have to consider. This is your resistance due to starting, and resistance due to acceleration. After the starting, gaining some momentum from speed is gradually increased. So that time, for gaining the momentum, picking up the speed, during the time, some resistance will take place. So that is given in the expression RAC equal to 0.028 W into V2 minus V1 divided by T. That means what? V2 is a velocity in kmph at the end and the beginning. Okay, so initial velocity, final velocity divided by time. This means rate of change of velocity. Okay, rate of change of velocity is actually acceleration. Okay, the acceleration into 0.028 into the load, so will be your the resistance due to acceleration. So this thing you have to consider. And another thing, wind resistance. Suppose some sections there will be heavy wind blow will be there. Those things, wind velocity also we have to consider. Considering the wind velocity and the surface area, exposed area. So with that, okay, we have to calculate the wind resistance. the expression is RW equal to 0.000017 A into V, where A is equal to exposed area in square meters and V is equal to velocity. Okay, wind velocity. Okay, wind velocity. Okay, so these are all the other resistance which are also supposed to be considered. It is all based on the situation. Okay, warranty. Okay, so to summarize, we have seen various tractive resistances, namely rolling stock resistance and drag resistance and atmospheric resistance. These three things are basically it is necessary to consider, because it is all running at a speed, at a higher speed. These all coming into play, but to consider. And resistance due to gradient and curvature, and is all occurred situations. So in the particular situation, based on the ruling gradient and based on the shortest curvature, it will be decided. Okay, this should be added. And resistance due to starting only, this will take place there. The speed will not be there. Speed criteria is not there. So, and resistance due to acceleration only due to speed picking up. So that time this resistance will come into play. And wind resistance, the area, the section where we have the heavy wind, those when it is critical, we are supposed to consider. Okay, so this thing and all, normally gradient will definitely will come across in the section. Curvature also will be there. This thing and all we have to consider, and this thing according to the necessity. And suppose in case of when we are preparing for an examination, the problem specifically they asked and they given the data, and using that you can include this one. Suppose the wind resistance, wind velocity they given, and surface area they given, so we can consider this one. Okay, so these are all the different type of tractive resistance you are supposed to consider for calculating the total load, how much the particular loco can haul based on the hauling capacity. Okay, is something about it. And coming to an example, some questions also they asked in UPSC Civil Service 2017. They asked. We can just see some worked out numerical example also. Okay, so the first question is enumerate the different resistances which a locomotive has to overcome before hauling a train. So you have to, whatever you discussed, that you can try different type of resistance. And a BG track locomotive having 4 pairs of driving wheels runs on a straight level track at a speed of 86 km, because only straight level track only they given. Okay, 86 kmph. The maximum axle load is 28.5 tons. Okay, so they given 4 pairs of driving wheels are there. Axle load is 28.5. The speed they given is 86 kmph, and it's a level track. The first case is a level track. Find the maximum train load that can be pulled by the locomotive, the level track. Permissible train load, how much it can haul. Second, they asked also calculate the reduction in the speed if the train climbs a gradient of only 200. Okay, with the load when it's climbing only 200 gradient, and what will be reduction in speed. And if the train climbs only 200 gradient with 3 degree curve, what would be the reduced speed of the train? So the coefficient of friction is 0.16 they given. Okay, so we can proceed here. The hauling capacity we have to find out. Solution. Given what they are given, the axle load they are given, number of axle they are given. I mean 4 pairs of driving wheels they are given. 4 pairs means 4 axles. Okay, they are given, and they are given coefficient of friction 0.16. With that we can find out the hauling capacity. So hauling capacity equal to coefficient of friction into axle load into number of wheel pairs. Okay, so with that we can find out 0.166 into 28.5 into 4, that is 18.92 tons. Okay, 18.92 tons is the hauling capacity. Suppose on a straight level track, train distance how much? Okay, level track only. So total resistance we have seen this resistance due to rolling stock resistance track resistance, then atmosphere resistance. Okay, so total resistance will be, we can calculate through this equation. Okay, now we are equating this hauling capacity is this much, 18.22, that site level the train resistance is this much. Okay, so equating the both, we can find out the how much load they can. Here is only the load is not given, unknown is W, but V they are given. We know 80 kmph. So equating the hauling capacity, you will be able to find out the train load, okay, including the weight of the loco. This is including the weight of the loco. Okay, we can find out. So 18.92 equal to this much. We are taking the W out, which is unknown. So substituting V, okay, velocity, that means speed, then we are getting finally the W equal to 18.92 divided by 0.0129. So that is equal to 1464.688 tons. Okay, say 1465 tons. Okay, this is the total load it can haul for this hauling capacity of 18.92 tons. Okay, so maximum train load that can haul in the first condition, no, this is 1465 tons. Okay, the second question is the reduction speed due to only 200 gradient. So the total resistance equal to, already we have seen three resistances, that is resistance due to rolling stock, then track, then due to atmospheric condition, plus due to 1 in 200 gradient if it come across the when train has to climb over 1 in 200 gradient, that is W into the gradient. So that you have to add. So now again equating the same, this 18.92. So now we are substituting everything. So already we got the load, how much it can carry, and only thing here we have to find out the speed. Here the speed we have to find out, because now we are carrying the load of 1465, but because of the gradient the speed has to be definitely the speed will come down. So and for this condition, what will be the speed we have to find out. So here is unknown is V, and finally we are having the equation like this is coming in the quadratic equation. So solving this, we are getting 54.68 kmph. So for hauling the 1465 tonnage of load for this hauling capacity loco, okay, when it is climbing over only 200 gradient, the speed will be 56.68. The reduction how much? When it is a level track, it is 86. When it is climbing over only 200 gradient, it is 55.68. So 30.32 will be the reduction, say 30 kmph. So reduction speed how much? 30 kmph. And third question is when the train negotiates 3D curve along with the only 200 gradient. So in this case, what we have to do here? So here one more distance involved here. Apart from the gradient, we have the 0.004 W into D. So this is due to the curvature. Okay, load into degree of the curve into 0.004. So this thing we have to equate. Again, for 18.92 it is hauling capacity. We are equating all the resistances. Okay, keeping the V so unknown. No, that is V. Again we will have the equation like this, and here when you are solving for V being a quadratic equation, V will come to 47.21. Okay, when the train is climbing over only 200 gradient along with the curvature 3 degree for the hauling capacity 18.92 and with the load of 1465, the reduction speed, okay, the speed what you are getting is 47.21. The reduction speed will be how much? 86, that is normal track, plain track, and minus 47.21. This is the speed it can run. It is on a curvature with a gradient of 1 into 100 equal to 38.79, say 38 kmph. This will be your result. Okay, this is something about this problem. considering these three main equations plus gradient and the curvature distances. Okay. If they specifically they given some wind force also, they given area, they given that also, we can consider and find out. Okay. So according to the problem what they asked, data they given, we can proceed. Okay. This is something about it. And next question, UPSC Engineering Service 2020 also they asked one thing. Here calculate the maximum permissible train load that can be pulled by a locomotive with 4 pairs of driving wheels with an axle load of 28.42 tons, each on a straight level track BG at a speed of 90 kmph. Also calculate the reduction speed if the train has to run on a rising gradient of only 200. What would be the further reduction in speed of the train as to take 3-degree curve on the rising gradient? Okay. Take the coefficient of friction to be 0.2. Okay. So they asked to calculate the same thing. The maximum load, okay, permissible train load, how much they asked, and they asked calculate to find out the reduction speed, the gradient only 200 and curvature also. Okay. The given coefficient of friction is 0.2. So again, similar we have to find out the hauling capacity coefficient of friction into axle load and number of wheel spans. Okay, 0.2 here, 0.2. Axle load is 28.42 into 4 pairs of wheels, and we are getting 28.74. This is your hauling capacity. And site level track, these three equations we are forming. Resistances. So total resistance because of the rolling stock and track and as well as atmospheric conditions. So we have the equation and substituting all here. We want to find W. We want to find out B already is 90 kmph. Here is unknown is W. Taking the W out, substituting B here, equating with the hauling capacity. We are finding out the total load that can be hauled. Okay, so that is coming to 1664 to say 1665 tons. Okay, the reduction speed due to only 200 gradient, total train distance equal to. So here along the earlier equation we are adding the gradient part, gradient distance, equating that. Okay, 28.74 the total hauling capacity. So here we are finding out the V, which is unknown, substituting the 1665 tons, for which we are calculating. For hauling 1665 tons, the hauling capacity of this much, and what would be the speed we are finding out. In case of gradient, only 200 gradient. So again, this will be your equation in quadratic form, and solving this one, V equal to 82.58 kmph. So the reduction speed how much? So in a normal plain track it is 90 kmph, whereas when you are climbing in 200 gradient, so it is 82.58 only. So 7.42, say 7 kmph reduction takes place. Okay. And similarly, when the train negotiates 3D curve on the above gradient, okay, only 200 gradient, the curve resistance also we are adding and equating with the hauling capacity, substituting the train loads, and V we are finding out. Okay, here 120 gradient, here degree of the curve is 3 degree. So substituting all, we are getting this equation, and this also in quadratic form, and here we are finding out the unknown V equal to 75.69. So 90 kmph in plain track, and subsequently along with the curvature, along with the gradient, the speed is calculated as 75.69. That is 14.71, say 15 kmph. So total reduction 15 kmph from the speed when it is running in a normal plain track. Okay. So further reduction speed, that means when it is in a gradient, the speed was 82.58, but along with this one, what do you call this curvature, so further reduction is 7 kmph. That means further reduction from the speed calculated for the gradient track is 7 kmph, and from the normal track it is 15 kmph. So this is the way. So we are calculating and we are solving for the total load the train can haul for the hauling capacity derived, and also the maximum speed that can go because of the effect of gradient, because of the effect of the curvature. Okay, there is something about it. Okay. Further, I would like to say, in case of high-speed routes where we are running, high-speed train and all, there won't be a speed restriction or because of the curvature or because of the steep gradient. Okay, because of the considering the gradient effect and the curvature effect, the hauling capacity will be fixed accordingly. The type of loco will be decided and will be attached. Okay, and if at all any speed restriction occur, that is because of the supervision inadequacy. Sometime, because of sharp curvature, not be able to provide the required supervision due to various reason and site condition, and there necessarily because there will be a reduction of the speed restriction. So otherwise there won't be speed restriction in case of curvature. Okay, and in case of goods train gauge section. So gauge section we have steep gradient and sharper curvature, and there will be a problem sometime. So because of the steepness, and there will be reduction in speed, and also that also sometimes will be managed by providing additional loco by double getting or by attaching one more loco or pushing. Hauling capacity will be managed. Okay, so this is practically sometime, and also you can just I want to show something about that different type of locomotives. On Indian railways we have diesel locomotives and LDCE locomotives. We have various locomotives and having different horsepower and the speed limit they are given. Okay, that is based on the section concern, based on the importance of the train and okay, the sectional speed, the loco will be decided, that will be attached. Okay, so this is the way it is being managed in Indian railway. Okay, this is something about the tractive resistances that we have seen in detail, and this is in what way it is just playing role in train running. Okay, whether we will conclude this video. So next video we will see something about the grade compensation on curves. So there also the curve distance and the gradient distance playing role. Okay, so thanks for watching the video. We'll see next video. Thank you.